Today, we're diving into a story of a near disaster that's absolutely fascinating. It reveals the incredible engineering that's designed to keep us safe up in the sky, but it also shows us what happens when just one tiny thing goes wrong. We're going to look at that razor-thin margin between total catastrophe and miraculous survival.
It all kicked off with these four little words. Coming from the cockpit of a passenger jet, well, that's probably one of the most chilling things you can hear. And for the people on Air Transit Flight 236, this was the start of an emergency that nobody could have predicted, thousands of feet above the middle of the Atlantic Ocean. The date was August 24th, 2001. An Airbus A330 is cruising along halfway from Toronto to Lisbon. But yeah, it would never actually finish that flight. See, over the Atlantic, its engines got starved of fuel. And then, one by one, they just went silent. This marvel of modern engineering became a giant, powerless glider. And the cause? It wasn't some huge storm or a big explosion. No, it was something so small you'd never see it. A single, tiny mistake that set off this absolutely devastating chain reaction.
So, to really get what happened here, we first have to wrap our heads around the sheer impossibility of the situation those pilots and passengers found themselves in. Just picture it for a second. You're 7 miles high, it's completely dark outside over this vast, empty ocean, and that constant, reassuring hum of the jet engines just stops. That was the shocking reality for the 306 souls on board Flight 236. They were now gliding, completely silent, with no power, losing that precious altitude second by second.
So the big question is, how on earth is that even possible? How does a state-of-the-art aircraft, a pinnacle of modern engineering, just run out of gas mid-flight? Well, to answer that, we first need to understand what should have kept it flying in the first place. Okay, so before we can really dig into the failure, we have to appreciate the science of what holds a massive airplane together. I mean, every single part is meticulously chosen and assembled to withstand some truly incredible forces. And the evolution of how we build planes it's just amazing. I mean, look at this. We went from basically wooden frames held together with glue and screws to these advanced alloy body panels fastened with thousands of super strong rivets and bolts. That leap in material science gave us structures that are not only unbelievably strong, but also surprisingly light, which, as you know, is pretty much the holy grail of aerospace engineering. And the materials themselves, they're like engineering superheroes, each one picked for a specific set of powers. They have to be light enough to even get off the ground, but durable enough to handle thousands of flights. They have to be tough so they resist cracking. They have to fight off corrosion. And they've got to handle these wild temperature swings, from a hot tarmac all the way up to the freezing cold at 35,000 feet. The point is, every single material has a critical job to do. But, just picking the right stuff is only half the battle. Before any aircraft design gets to carry passengers, it has to go through this absolutely grueling series of tests to prove, beyond a shadow of a doubt, that it is safe. And this whole process is just a masterclass in being careful. It all starts in the digital world, with really advanced computer simulations. We call it computational fluid dynamics, or CFD, to basically predict how air is going to flow over the wings. Then they move into the real world. They start with scale models in wind tunnels. And only after passing of those tests do they build a full-scale mock-up for the final checks. Each step is designed to find any and every flaw before that plane ever leaves the ground. And that brings us to the most important part, because this quote here just nails it. You can run simulations, you can test models for years, but the ultimate proof, the real acid test, is taking that full-scale machine out into the messy, unpredictable real world. It's the only way to know for sure how it's going to perform when things get tough. Right, so if these planes are built so well and they're tested so rigorously, what in the world went wrong on Flight 236? Let's get back to the scene and look at the anatomy of this specific failure. And the root cause it's almost frighteningly simple. It all started 5 days earlier, during some routine maintenance. A mechanic replaced a hydraulic pipe with the wrong part, one that was just a tiny bit oversized. Now, that tiny error meant this new pipe was just barely touching a fuel line next to it. And for 5 days, with every little vibration from the engines, it slowly, silently rubbed a hole right through it, until, bang, the fuel line finally gave way mid-flight.
And from the pilot's perspective, this timeline just shows how terrifyingly fast it all fell apart. It starts with some strange fuel readings, then a direct warning, fuel imbalance. They know something is seriously wrong and immediately divert to the Azores Islands. But it's a desperate race against time. The right engine, starved of fuel from that leak, just flames out. Then, only 13 minutes later, the left engine cuts out. They had tried to cross-feed fuel from the good tank to the starving engine, but what that actually did was accidentally drain the good tank even faster. And just like that, they were a glider, thousands of feet over the dark Atlantic with absolutely no options left.
You see, that one little maintenance mistake basically threw the plane to the wolves. It exposed it to all these forces that engineers are always fighting against. So beyond this one error, what are these constant enemies that all of engineering is trying to defeat?
Well, engineers kind of personify them like this. You've got heat from the engines and the friction of the air itself. You've got pressure pushing on the inside of fuel and hydraulic lines. There's constant vibration from the engines, which is exactly what caused those two pipes on Flight 236 to rub together. You've got shock from things like landings and turbulence. And finally, abrasion. That's just the physical wearing down of surfaces by friction. Every single safe flight is a win against these forces.
So, that brings us to the most important point. Knowing all these enemies, how do we build systems that can reliably beat them? How do we stop one small mistake from turning into a total catastrophe?
The answer is a multi-layered defense system. You have checklists to prevent simple human errors, like installing the wrong part. You have standard procedures that give pilots a clear, proven plan for any emergency. You've got backup systems to provide redundancy. And you have planned maintenance, which is designed to replace parts before they ever get a chance to fail. On Flight 236, that very first layer, the human process, the checklist, was breached. It was then up to the skill of the pilots and the fundamental design of the aircraft to save the day.
So after looking at the advanced materials, the insane level of testing, and all these layers of safety procedures, it really boils down to one final question. What is the single most important tool in an engineer's or mechanic's or a pilot's entire toolkit? It's this: vigilance, the human factor. It's the discipline to follow that checklist every single time, to double-check the part number, to question a reading that just looks a little bit off. The story of Flight 236 is such a powerful lesson. Even the most brilliantly engineered machine is only as strong as the human systems that are there to support it. And in the end, it was the incredible skill and absolute vigilance of the pilots that turned a catastrophic failure into the longest and most successful powerless glide in aviation history. It's a real testament to that partnership between human expertise and amazing engineering. And that is definitely something we're thinking about.